Hello everyone, welcome back to Historical Geology 1404. Today is lecture 7. We talked about life, the ways that life can change, and we are going to continue that conversation next week when we meet again, but today we're going to take a little break on that to talk about how we correlate things in the rock record, because that's relevant to the ways that we track the progression of life through time. Where do we find evidence of life? What do we call evidence of life in the rock record?
Fossils.
Fossils. And where do we find the fossils?
In rock.
In rock. So yes, naturally we need to understand about the record of rock for us to be able to interpret the fossils we find in them. Sounds right? Makes sense. Before we get started, any questions or comments or interesting stories or anything like that you want to bring now that we are on camera? Remember, we are recording this. Yeah.
I think it was like a year ago. I was walking down the sidewalk and I found it looked like a skeletal turtle that was on the street. It wasn't in any rock.
Yeah.
But it was just straight skeleton, and I didn't know that. It looked like it was already slightly fossilized because it was already really decayed.
Yeah. So it won't have been fossilized. He found a dead turtle shell with a skeleton in it, right? Wasn't fossilized. What happened was it here in town?
Yeah, it was in my neighborhood.
Okay. So you guys know the duck pond over by in downtown across from the mall?
I tried to go fishing.
Did you get a ticket?
No.
Okay.
You can fish there.
I wouldn't need anything out of that.
It says you could legally fish there, but there was no fish.
Have you seen that water, bro? It does not look healthy. It does. Yeah. Well, they only stock it every now and then, like every couple of years, I think. It costs a lot of money to stock that thing. Put 10,000 more fish in there is it costs the city like $500,000 or something like that. So, the duck pond has 2 species of turtle in it that I have observed, red-eared sliders and ornate box turtles, which are the species I have in my zoo next door. Both of those turtles I found as fresh hatchlings at the duck pond.
Yeah, it was a box turtle that I found.
Right. So he found a box turtle. So what happened there was this turtle died and then it got eaten by a combination of probably ants and bacteria. Ants can strip a skeleton clean in a couple of days.
Ants?
Yes.
That's scary.
Yeah. There are going to be a few other things that help along with it. If the skeleton was still in the shell, then nothing big like a coyote found it, which is pretty rare, or a dog or a cat. Those will also eat away at it. But if you found the skeleton still in the shell, then it was pretty much just ants and other small organisms that ate it.
Until my dog stepped on it.
Yeah, there you go. So only small critters that could get in the shell and strip the skeleton clean found it and started eating it then. Mm-hmm. Right.
Yeah, I was walking my dog, and every time we would walk past him, he just did not want to leave it alone.
Yeah. How big was it?
Well, I want to say it was this big.
Yeah, so full grown. Ornate box turtles like Algernon that I've got next door, they'll get about the size of a Big Mac, about there.
My favorite.
The red-eared sliders, though, if any of you have seen, just since the start of our semester, my red-eared slider has gotten big. When I got him, he was the size of a quarter. And now he's this big. And he's only 5 months old. So he's getting big fast. I actually just had to get a brand new aquarium tank for him because he's getting way too big for the one I had him in when he was a baby. I'll probably swap it out over Christmas break. Yeah, interesting story. Anything else we want to talk about? Yeah. Hold on a second. What was that? Sorry.
Are you going to have work during Thanksgiving break?
Am I going to have what?
Work for us?
Work for you during Thanksgiving break? That depends on how much work you get done before Thanksgiving break.
Is there any work on, you're going to give on Thanksgiving?
Like that I'm giving you specifically for Thanksgiving break?
Yeah. You sign something that
I mean, I never give out specific Thanksgiving homework, but I may give you an assignment when we meet before that, and whether or not you finish it before Thanksgiving break is up to you. Let me work this out in my head, okay? So today is lecture 7, then there's 8. 8 right there. And then the exam 2 review, and then 9, 10, 11. Okay, so 12 won't be until the next week. So, I mean, I don't think that I have any particular assignment that I'll give you over Thanksgiving break. You'll obviously still have a lab you can work on, but whether you do it before the break begins is up to you. Yeah. Reflections? Yeah, what about it?
What's the top reflection you've seen from a rock?
Like my favorite reflection? I mean, a reflection is an image of the original object. So you're essentially asking what my favorite object was? So, okay, so my favorite scene that I've ever seen, my favorite reflective thing was I was up in a high mountain range this would have been in Colorado. And there was a lake up there, and it was a beautiful clear day, and there was a snow-covered like peak right here, and the lake was right underneath of it, and there wasn't a single bit of wind, so it was perfectly flat lake, and the reflection of the mountain and the mountain itself like perfectly merged into each other.
Wow.
Yeah, very vivid. I remember there was like patches. I was so high up, it was June, but there were patches of snow around me because of how high up I was.
That's very nice.
Yeah, oh, beautiful. Colorado, Colorado. Yeah, some of the most beautiful scenery you'll ever see in your life in Colorado. I would live in Colorado if it wasn't like 5 times more expensive than everywhere else.
It snows a lot over there, huh?
Well, yeah, because it's very high in altitude. A lot of the state is.
So it's mainly like, of course, cold, like instead of it being mainly hot.
No, it's mostly cold. Even in summer, it can get pretty chilly. Or way chillier than it does here anyway. Okay. Other questions? All right. I'm going to start off today by talking about some of the guys who laid the groundwork, pardon the pun, for the geological principles we're going to talk about today. Okay. Specifically, the action, or I should say the science of observing the geological layers and interpreting them for the data that we can pull from them now. Okay? Starting off with Nicholas Steno. Lived in the 1600s. Only lived to be 50 years old, which was actually a pretty ripe old age for the 1600s. If you lived to be 50, you were doing pretty good. Okay? So he was Danish. He started off as a scientist, where he would, or natural philosopher, somewhere between that, where they were at that point in time, where he would observe things. He wanted to answer questions about the world. So he would observe things, and then he would try and find reasonable explanations for them. He actually helped develop the principle of superposition, which we also call the principle of superposition, which is what? Yeah, oldest on bottom, youngest on top. Remember that? Then there's original horizontality. Do you remember what that is?
Say that again?
Original horizontality.
Like everything is horizontal.
When? And what? Everything? Am I horizontal?
Plants. Or no, rocks. Like whenever they stack, they go up.
Right, they pile on top of each other horizontally, right? It's very difficult to make layers of rock or layers of sediment, pile them on top of each other at an angle like this. Doesn't happen that often. Definitely not on a large scale. Originally horizontal. That's how those layers stack. Okay? So he helped develop a lot of these principles, as well as starting to theorize about where fossils come from. Okay? Think about it. If you're living in the 1600s and you see a skeleton in rock, what are you supposed to think about that? Somebody died there? Yeah, but why is it in the rock? And what if it's a dinosaur, not a person? What do you think about that?
Died a long time ago.
Huh?
Died a long time ago.
It died a long time ago, but I mean, hey, what's happening right now in the 1600s? James Ussher is what's happening right now. And James Ussher is the guy that said Earth, not that Usher. Remember, I even had a funny picture about it and everything, right? Not that Usher, no. This is the usher who said that the earth is 6,000 years old based on dates he found in the Bible. Right? This is going on in the 1600s. So, during all of this time, how do I put this lightly? Christianity was far more aggressive towards science and making sure that everyone towed the line. Even going so far as if you disagreed with the Catholic Church, you were sentenced to death. Happened quite a lot. Scientists, lots of scientists during this time were put to death or committed suicide because they were facing terrible tortures from the biggest powerhouse in the world, which at that point was the Catholic Church. If you disagreed with the Catholic Church, it was basically a death sentence. So Nicholas Steno started off as a scientist and then ended up becoming a clergyman. He ended up leaving science behind in favor of preaching, which, entirely fine. I don't actually know what his motivation was there. I don't know if it was self-preservation because he started asking questions that were contrary to popular doctrine at the time, or if he genuinely felt like it was a better path for him to go in. No judgment either way. But he eventually he left the sciences behind and started doing teaching in church and all of that. But before he left, he did make these very valuable contributions to the world of growing sciences that were going on at this point in time. Later on, we had William Smith. He was an English surveyor. Who can tell me what a surveyor is?
You like make the maps?
They do make maps. Do you know what?
They like define the land beforehand.
Right. The job of a surveyor is to calculate dimensions and scales for things like making maps. Are you ever driving down the road and you see those guys with the yellow safety vests and maybe they've got hard hats on, but they've got these things on tripods. And there's this guy on one end that's looking like through a telescope, and then you keep driving and like half a mile down the road, there's another guy just standing around on his phone because his only job is to make sure that this other thing on a tripod stays still, right? Those are surveyors. They are measuring a length of road, calculating the exact length of that road. Usually what that means is they're going to expand that road a little bit, right? They're going to push the shoulder out or something like that, and they need to know exactly how much space they need and how far so that they can put together a quote for a contractor to come and do it, right? We have this much road we need to do, and then the contractors can look at that and say, I can do that for this much money. But you need a surveyor to do that first. You need surveyors for things like construction. You need surveyors for destructive things, like if you need to demolish a building. If you're going to blast a highway through a mountainside. If you just need to calculate the exact dimensions of your property, you would hire a surveyor to do it. Okay, so surveyors, we still use them today. So back in the 1700s, when this guy was around, right, he was a surveyor in England. Now, they didn't have the fancy lasers and stuff we do now. He did a lot of footwork. He did a lot of manual measuring, which means that he had hands and feet-on experience with a lot of the English countryside. And you know what he started to find out? You know what he started to see? This layer of rock looks a lot like that layer of rock I saw on the other side of the country. And they both have the same fossils in them. How interesting. So after a while, he started keeping careful notes of all of these similarities. And eventually, he actually put together a map of all the exposed layers of rock that he saw that were the same ones across the entire English countryside. And this is a picture of it right here. This is the first ever geologic map. He made this of England. This is the whole country of England. Now, we've since redone this, and it's way more specific. He did a lot of generalities there, but he was just working with what he had. He didn't have a professional geological education. He was just a dude that was really good at math and scales and distances and was super curious about geology. Okay? So he was able to put this together. And this is still geologic mapping is still something that we use today, right? Very important. But he actually took the time to put this together, and no one in the scientific community saw the value in it until he was pretty much already dying. He was on his deathbed. Yeah, sure. He was on his deathbed before the scientific community acknowledged, you know what, this is actually a pretty useful tool. Thanks, bud. Right? That's unfortunately very common with scientists. What this also allowed was for the beginning of the principle of fossil succession, which you may recall allows you to generally relate layers of rock to each other, not only vertically, so through time, but also across distance. This layer of rock to that layer of rock. Fossil succession. Why? Well, because this layer has one fossil, and this layer has that fossil plus another one, and this one has the second one, but not the first one. We can see the sequences of fossils appearing and disappearing. Okay? Georges Cuvier. You want to guess what kind of name that is? Ah, good. You can read. All right, I put it up there. Well done. Okay. Naturalist. Do you remember what I told you a naturalist is? A naturalist is someone who studies nature, but not within one particular discipline. So when you see the term naturalist, that usually means someone who is equal parts biologist, chemist, physicist, geologist, all of those things. Okay? So his contributions to sciences in general are quite broad, but his contributions to biological and geological sciences pretty much are within the bounds of fossils. He provided a lot of theories about fossils. Now, he wrote quite a bit and theorized quite a bit about the nature of fossils, how fossilization can occur, why it occurs, how long it takes to occur, and how long ago these animals were. He just had one flaw in all of his theories. He was a catastrophist. Do you remember what a catastrophist is? Huh? Everything bad is going to happen? No, that's called a nihilist. A nihilist is someone who's like, what's the point? Everything's going to die and get destroyed anyway. Right? I want everything to get destroyed. Get it over with. Right? No, a catastrophist is something different. Did you have your hand up?
Oh, no.
Oh, okay. Catastrophist. What is a catastrophist? You remember?
Someone that exaggerates.
Exaggerates? No. That's a drama queen. Or king, you know. Dudes do it too. Huh?
I said mostly queen.
Oh, okay. We're not going down that road right now, okay? All right. All right. Yeah, taking his life in his hands with comments like that. What about natural disasters?
I guess it's like a volcano. They cause destruction.
Yeah, natural disasters cause destruction. Basically, catastrophism is the belief that all of the large features that we see today are the result of extremely catastrophic events. This was before the concept of how old the Earth was, and therefore, the only way that something like a mountain range or a valley or a volcano or these other big features could form is through very rapid, intense events, because they just simply could not comprehend small processes over long amounts of time causing them, right? The only answer was something big happened. A massive earthquake ripped a crack in the earth and made this valley, right? That's the only answer that made sense to them, and that was catastrophism. All right? Now, his belief in catastrophism really skewed his perspective on what fossils could be and how old they could be. He still theorized that they were pretty old. But people... Are those tortillas? Those look like really old tortillas. Those are rock hard. Those are Frisbees. Okay? Don't eat those.
I'm not. Me and my friends been doing the slapping game where we play bucket scissors, and if you lose,
You're going to put someone in the hospital if you slap someone with those. Just put them in water? I don't think that's going to work out well. Okay. Bless you. Okay. Yeah, so because the Earth could not be very old, that really skewed his perspective on the age of fossils as well. So we do owe him a lot for the theories that he put together about the age or the process of fossils and the fact that they come from lifelong dead, but he held himself back, not to his own fault. I mean, the principles of how old the Earth actually is hadn't come around yet, at least not until Hutton and his work were popularized. Hutton lived at about the same time. They overlapped in different parts of the world. French, Scottish, not too far from each other, but it takes a while, especially at this point in time, for information to percolate around. And Hutton's information did not get accepted by the scientific community until he was almost dead. Yet again, classic story, right? So it would have taken a while for that sort of thing to percolate over to this area. Let's talk about Hutton. Hutton is one of the fathers of what we call the principle of uniformitarianism, right? This is also known as actualism, by the way. You may see it referenced that way. Can anyone remind me what the principle of uniformitarianism is? It's something that I had you write down word for word back in 1403. That's a good summary. Things that happen in the past happen in the future, but more. Okay, we're talking about the additions that I told you about, but the actual basic word-for-word definition of the law of uniformitarianism minus what Mr. Hart adds at the end. Yeah. Here, listen.
Physical, chemical, and biological laws that operate today also operate in the geological past.
There you go. Physical, chemical, and biological laws that operate today also operated in the geologic past. What does this mean for catastrophism? If I'm not observing any massive catastrophic events right now, but I am observing the small, slow processes, what does that mean for catastrophism? The answer must not be in large, massive, catastrophic events. The answer must be in the small processes we see now over long periods of time. An earthquake did not rip that valley open. That river at the bottom of the valley ripped it open over 4 million years, you know? It took a long time for these small, slow processes to work, but work they do. I told you the rate at which a tectonic plate moves on average is about 5 centimeters a year. That's how fast your fingernails grow. Does that seem quick to you? No, but the Earth doesn't care. The Earth doesn't think. The Earth exists over periods of millions of years. How far will that tectonic plate have moved in 1 million years? 5 million centimeters. Is that a bigger number? Yeah. Yeah, it is. That's noticeable. Right? So, principle of uniformitarianism spits in the face of catastrophism. Catastrophism has a firm hold on the world right now. So yeah, Hutton and his data and his conclusions, they're kind of like, ha, we don't know what you're talking about. What do you do for this? Right? Until later on in his life. And then he was accepted because people actually realized, oh, shoot, this guy's got the receipts. Like, he knows what's up. He knows what he's doing.
That's a lot of feet.
Do the math. How many feet are in 5 million centimeters, bud?
64,000.
164,000. That's a lot of feet. It's a lot of feet. Okay. All right. You may remember this exercise, so you don't necessarily need to do it with me again, but I'm just going to remind you about how we break up geologic time, okay? You remember this, when we did this? Yeah, so we have this box, we divide it in threes, then we have these biological events that occur in our lifetimes. Every now and then, I'll have someone who's like, Professor Hart, I never learned how to ride a bike. Yeah. I'm like, well, put something else there. When I don't know. When did you learn how to ride a scooter? You don't know how to ride a scooter? Okay. All right. You walked that back pretty quick. All right, and then we've got our numerical time, which you each put your own dates on there for. Then we have sequential time, which is when we separate this into different ages based upon events, right? So everything that occurred in my life before I started going to school, I call the pre-Schoolian. Everything in my life after I started going to school on this timeline, I call the Schoolian. Notice something. What is missing from my school record here? Way before that.
First grade.
I'm missing first grade, second grade, kindergarten. Clearly, I did not immediately go into third grade, right? That doesn't usually happen. But what if this is a fossil record? And, I just thought of this. What if I have a photo album of my childhood? And that's what I'm drawing all this off of. That photo album is like my geologic record. It's like my fossil record. Evidence of the things that occurred in my life, right? But I don't have any pictures from kindergarten, first grade, or second grade. The first picture of school I've got is from third grade. That's the only evidence I have. Therefore, yes, that is when the Schoolian would start. Not because second grade, first grade, or kindergarten existed. I don't have evidence for when it did. Does that comparison make sense to everyone? Good. Bear that in mind because our fossil record is absolutely incomplete. There are gaps. Why? Because fossilization does not occur everywhere, and it cannot occur to every organism. Very few ever get fossilized, and most things that lived on our planet never were in a situation where they even could get fossilized. Just bear that in mind. So here is our geologic time scale. We have biological events that were the time intervals we just talked about. The years, that's the numerical time. Sequential time are going to be our eons, eras, periods, and epochs. Okay, here's that time scale. You can feel free to use this time scale, by the way, for your labs if you have not found one online that you like. Feel free to use this one. Let's talk about each one of these intervals, okay? Each one of these units. Eons, these are the largest ones. The Precambrian is generally referred to when we are talking about the Hadean, Archean, and Proterozoic eons. 3 distinct eons grouped within the Precambrian. Why do we put them together? At the beginning right here, at the Cambrian, something remarkable happens. Let me back up to that other slide that we were just at. Right here. Rise of all major animal groups. Life is abundant, trilobites dominant, first fish, no known terrestrial life. Right here at the Cambrian, about 543, 541, they're still pushing that further and further back all the time, it seems like. About there is when we start to see not just bacterial life, okay? Other things show up. Things that we see in the oceans today show up then, okay? So right here, at the end of the Proterozoic and the beginning of the Cambrian is where we draw this first line between eons. At that point, the Proterozoic ends and the Phanerozoic begins. And you know what? We're still living in the Phanerozoic, okay? The era of modern life. The Hadean lasted 500 million years. The Archean lasted 1.5 billion years. The Proterozoic lasted 2 billion years. Look at this. These look way smaller than these, but that's only because relatively little happened. We don't have much record, and definitely not much fossil record from that time. This represents 4 billion of the 4.5 billion years that Earth has been around. The other 500 million years is represented here. But this, if this were to scale, would be way longer. Okay? Yeah. All right. Think of it this way, if any of you are football fans. If I stretched the entire geologic time scale out across a football field, This part, all of this would not begin until you were at the beginning of the far end zone. You'd have to walk all the way from one end zone, the far end of one end zone, all the way across the field, and at the beginning of the next end zone is where the Cambrian would begin. Okay? About there. Maybe a little closer, but you get the idea. I'm trying to give you a sense of scale. Oh, I never finished talking about stuff. Eras. Eras are the next unit here. The Paleozoic era, the Mesozoic era, and the Cenozoic era. Paleozoic era, think of that as early forms of life, okay, of multicellular non-bacterial life. In the Mesozoic, we call it the age of the dinosaurs, the Triassic, the Jurassic, and the Cretaceous. Then we live in the Cenozoic, the age of mammals. That's our time, okay, way up there. Then we have periods. The Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, Quaternary. Those are all periods. Okay? Then we have epochs. And we can divide all of these periods into epochs, and many of them are. We are just going to talk about the ones most relevant to us in the age of mammals. Okay, so later on, we're going to discuss the Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene, which are the periods relevant to you and me here in the Cenozoic era. Would I say dinosaurs were real?
Yeah.
Yes. You know why?
Why?
There's evidence. We have evidence. We have their bones. I've got bones, teeth, claws. I even have dinosaur poop out there in the display cases.
Really?
Yeah, it's called coprolites. Coprolite is fossilized poop.
But is it dinosaur poop?
Yeah. Yeah, we have dinosaur poop
How do you know it's dinosaur poop?
because of how old it is and what is in it. Also, reptile poop is very different from mammal poop. How do I describe this? Remember I was telling you about Diablo's hole called a cloaca? He only has one. Reptiles only have one hole for pee, poop, and sex. Okay, it's called a cloaca, right? They don't separate, most reptiles I should say, don't separate pee and poop from each other, which means that it comes out as a sort of paste or slurry. Okay? We have to assume dinosaurs had the same, but you know what? It's hard to know because soft tissues aren't really fossilized. And yet, reptiles now have cloacas, as do birds, which are descendants of dinosaurs. Therefore, we must assume dinosaurs also only had one hole, the cloaca. So dinosaur poop is going to be structurally different than mammal poop, which is separate from the urine. It is not as watery as reptile poop. It's more solid, mammal poop is, right? So we can see structural differences between what is dinosaur poop and what is mammal poop from back then. That's way more you wanted to learn about poop and cloacas today, but hey, you're in a science class. All right? You know, whenever people ask me, do you think megalodons are still alive? Or do you believe in Bigfoot? Or do you believe in the Loch Ness Monster? You know what my answer is? Show me the poop. If those things are alive right now, show me the poop. Everything poops. Literally everything poops. Bacteria poops. If something exists, it's going to leave poop behind. Show me the poop, and I will believe it's real. No, I'm just kidding. I was going to say, is Santa real? But show me the poop.
Show him the poop.
Yeah, what's your question? It would look like much bigger great white shark poop, yeah. Why what? You think great white sharks are going to come together and have a poop party or something? And like, you know what would really freak out those humans? If we all came together and pooped at the same time, so they think it's megalodon poop. They would do that, right? The largest great white shark ever found, I want to say, was 26 feet. Yeah, it's pretty big.
That's like this beard in there.
What's that? Yeah.
Adult silkworms.
Oh, okay. So their waste gets excreted a different way, though. Okay, everything excretes. How about that?
So it's 1 feet to like from the floor to the roof.
That's because they're parasites in other things' digestive systems. What's up?
So like is like 27 feet from like here to the roof.
No, it's way higher than that. Way bigger than that. Yeah, no, here to the roof, this is a 12-foot roof.
What?
How about from downstairs to third floor?
From this ceiling almost halfway through the next floor should be about 26 feet. From floor to floor in this building is 30 feet, I want to say. And if I remember correctly, the biggest great white shark was 26 feet. Someone could fact check me on that if they want. I want to know the right answer. I just seem to remember it being... But what I'm trying to get at is megalodons average between 40 to 60 feet, depending on size and sexual dimorphism, which is males being larger than females or females being larger than males. We're still not sure which was which.
It
What?
says it was 20 feet long.
20 feet?
Yeah, 20 feet.
The largest one.
Yes, the largest one.
I could have sworn I heard about one that was way bigger than that.
He just liked it.
It's the largest great white, right?
Yeah.
Yeah,
20 feet?
20 feet. And
Okay,
it's
well then.
blue.
A megalodon would be 3 times larger than the largest great white shark ever found. Mm-hmm. Yeah,
Is there a shark?
you may. I contemplated putting that the Meg on our watch list as well. No. Okay, because while it does concern ancient sharks, which we are talking about, the rest of the movie is highly irrelevant.
Huh?
Right?
But the part where they kill the shark is like,
Right, it's an action movie that the antagonist is an ancient shark. Jurassic Park, Ice Age, The Core, these are all things that we actually, most of the movie are concepts that we spend talking about in the class. So while The Meg is a fun movie to watch, there wouldn't be a whole lot more to make fun of other than this movie's dumb. Right? Okay. All right. Right. So moral of that whole tangent, show me the poop. All right, so how do we determine those boundaries? Where do we draw those lines? Where does the Devonian end or begin? Where does the Silurian end or begin? Biological events. That's the big thing, okay? Let me go back. I know I keep coming back to this, but it's because it's important. Look at this. First, spiders, scorpions, centipedes, early insects, vascular plants, jawed fish, and large reefs appear. That's a huge line. That's a huge development in life. And so yes, we draw a line there. First, amphibians. That's a huge thing. Whoop, draw a line there. First, reptiles. That's a huge thing. Whoop, draw a line there. Major events in the history of biology on Earth are why we mostly draw these lines where we do. Then, extinctions. The disappearance of life as well. Now, consequently, to extinctions. First of all, tell me what an extinction is, somebody.
Remember, there's no more of an animal or no more of something
Why would there be no more?
because they die out.
There is some die out. A single species disappearing, we don't call that an extinction. There has to be a substantial quantity of things that die off due to an event or a process for us to call it an extinction. Okay, there are several massive extinctions in Earth's history. Don't worry, we are going to talk about all of them. Yeah, you may. We're going to talk about all of them later on in the course in Module 3. We will learn about all these extinctions. However, after every single extinction is what we call an adaptive radiation. Again, something we will discuss later. But essentially, do you remember I told you about niches? What is a niche? We learned about this last time on Tuesday. A niche is like an available apartment in a building, right? That's how I described it. Everything occupies a niche. All apartments must be occupied. It is a space within an ecosystem that an organism occupies. In an extinction, niches are left vacant as things die. And so the survivors are going to adapt, they're going to diversify, they're going to spread into those other niches. Okay? That's what happens in an extinction. After an extinction, we get this big adaptive burst in the remaining life. Okay? Then there's lithology. Lithology being the type of rock. If there is this particular sequence of rock that we can see continues for a while, we will draw lines based off of that. An abrupt change usually means an abrupt change in the environment, and we might draw a line in our geologic layers based upon those abrupt changes as well. Okay? All right. So what are some of the things that cause us to make these changes based off of biology? Changes in abundance, which, hey, remember our conversation about index fossils? These all have to do with index fossils, right? Remember that. So here, at this line, where the Precambrian ends and the Cambrian begins, we go from seeing barely any life, just kind of wandering around in places, to, boom, life is everywhere. That's why we draw that line there. It's such a big change, bless you, that we even make a different eon out of it. The Phanerozoic picks up right there. Okay? Changes in diversity as well. Changes in diversity are great because the more different forms of life you have and the quicker they live and die, the better they do for index fossils. The more index fossils we have, the easier it is to correlate life across time. Remember William Smith, that surveyor guy I talked about? He laid the foundation for this sort of study by making all the observations about fossils he did and making that geologic map. He realized that fossils aren't just random. You can go to this layer here and find fossils X, Y, Z, and go to this layer over here and find fossils A, B, C. They're not mixed, which is very important. Because if they were mixed, that would mean everything was living at once. By finding layers of rock that contained one type of life but not another, he essentially said, or proved, there is a sequence to life through time being the important thing there, the important factor. Okay? The study of geologic units is called stratigraphy. You all have some experience with stratigraphy. Who enjoyed Lab 2? Who's finished Lab 2? If you have not, really try to get that in today because you should be working on Lab 3. Okay? Lab 2 is all about stratigraphy. Essentially, studying the sequence of layers of rock, and we can use that sequence to interpret some things. I haven't taught you how to interpret that. I'm going to get to that here in a little bit today. There are different ways that we can use stratigraphy, though. It doesn't all have to do with the type of rock. I'm going to talk about those in a minute. But yes, sorry. But the different fossils and layers of rock that we see provide correlation tools. Correlation allows me to interpret what happened between A and B. If this is present in layer A, and the next layer above it does not have that thing present, something occurred during the time between to remove the presence of that thing. What was it? Let's find out. That is the essence of stratigraphy. Now there are different types of stratigraphy. Chronostratigraphy. This is if I am simply interested in delineating the time between my units. I don't necessarily care too much about the other factors there. I'm only worried about figuring out the difference in time between layers, particularly within a given interval. That's chronostratigraphy. Biostratigraphy is when I separate layers or units from each other based upon their biological content, or fossils, right? We've already seen how you do this when we talked about index fossils. If I have fossils that occur in one layer, and then something happens and I don't see them all in another one, I will draw a line. For example, look at this. Each one of these lines represents a certain species. When the arrows are pointing down, that means that that species existed longer ago, and as time goes on, they reach this line right here. Arrows that are pointed up mean that species continues past that point. Look what happened right here. How many species, how many of their lines stopped right there? How many species end right there? Quite a few. What I'm looking at between these two layers might be described as an extinction. Because we have so many that come up here and so few that continue past it. Some sort of event caused an extinction there, right? That is called biostratigraphy. Essentially mapping first occurrence of an animal to the last occurrence and figuring out why and how and everything in between by using that sample and others. These are your requirements for an index fossil right there. Again, we already talked about that. Magnetostratigraphy is interesting. We learned already about how Earth's magnetic field causes iron minerals to reorient relative to wherever north and south magnetic are, right? It doesn't care about geographic magnetic north. It only cares about magnetic north. Wherever it is, in whichever pole, because remember they will switch every now and then, my iron minerals as they form in the ocean are going to orient relative to that. Magnetostratigraphy is separating the layers of rock from each other based upon their orientation to magnetic north or south. This is how we get these crons, which tell us how our magnetic field has swapped in the past. That's magnetostratigraphy, separating layers of rock from each other based upon magnetic orientation. Lithostratigraphy, we already talked about this one, right? Lithostratigraphy is simply separating layers based upon rock type. Fossils, largely irrelevant. Like in your lab, I didn't make you identify any fossils or separating any layers of rock from each other based on fossils. That's biostratigraphy. Lithostratigraphy is simply concerning yourself with the type of rock and the structures present there. Like you learned about cross-bedding and stuff like that. You also learn about mud cracks and ripples and everything, right? Those are relevant to lithostratigraphy. Any questions about the different types of stratigraphy? All right. So before we knew about radiometric dating, there were a couple of ways that people tried to figure out how old the Earth is. This is actually something that someone asked me on Tuesday, I think, was how did the ocean get so salty, right? Yeah, it was very relevant because now we're talking about the similar subject. How did the ocean get so salty? Well, I pointed out sodium and chlorine are very common ions that we have here on our planet. They bond together very easily because they satisfy each other's octet rule needs. And so we get a lot of it. And most of it ends up getting washed out to the ocean because it dissolves easily in water. Yeah, sure. Okay. At one point, people were asking, well, how salty the ocean is should help us figure out how old the Earth is. If we measure approximately how much salt gets washed out into the ocean every year, we should be able to work backwards and figure out when that process started. Does that sound reasonable? Well, sure, but what does that assume? There's a very large assumption here. No, it assumes that the ocean started out fresh. For you to be able to measure backwards through time, you would have to assume that the same approximate amount of salt is always getting washed out to sea throughout all that time, and you have to assume that the water in the ocean started as fresh water, right? Those are massive assumptions that did not work out. Next one, what about the cooling of the Earth? That was a little more scientific, a little more interesting. The Earth is cooling, right? So if we measure how long it would have taken for Earth to reach its current rate of coolness from a liquid ball of rock that we used to be in space, shouldn't that tell us how old the Earth is? As it turns out, it doesn't. Why? What are the assumptions here?
Because it might have not been the first time I'm talking.
That's a good point. What if we started the melting process again? And as a matter of fact, we did when we got hit by Theia, right? That other planet. We remelted the planet and started that all over again. What else? It's okay if you read them off the slide as long as you explain them to me. Is Earth the same material from the top to the center? From the outside to the center, I should say. No, it's not. We've learned about the differences in composition between Earth's materials in its layers. To assume that the cooling rate of the Earth has been consistent throughout time is to assume that it's the same material from outside to center, but we know it's not, which means that cooling rates are not going to be consistent. That's the first assumption that we have to break. Second one is, we know that the material inside our planet moves. Convection. What does movement generate? Heat. Bingo. Also, we've got all the radioactive decay going on inside our planet. So not only is Earth not cooling off at the rate that it would, but it's continually receiving more energy from the radioactive decay. So we also cannot calculate the age of the Earth that way. So how do we calculate the age of the Earth? Through radioactive decay. Why? Because radioactive decay is consistent, measurable. I've told you this before. The half-life of uranium-235 or any other radioactive element, remember a half-life being the amount of time it takes for any volume of that material to decay into a daughter isotope, okay, a stable isotope, it's going to be the same everywhere. Uranium-235 will decay over the same half-life here as it does on Mars, as it does in the Andromeda Galaxy, as it does on the other side of the universe. It will always be consistent. Okay? Uranium-235. No, it's 234. 235, 704 million years. 238, 4.6 billion years. Rubidium, 87, has a half-life of 48.8 billion years. The half-life for rubidium-87 has not passed yet. We're only about halfway through, less than halfway through, maybe a third of the way through, the first half-life of this radioactive isotope. They're still decaying towards their first half-life. These are things that we can measure the ratios of to determine the age of everything in our universe. And we do. Radioactive dating. That's what that is. Fossils are great for providing dates. Relevant only here on Earth, obviously, for now. Fingers crossed. But also, they don't provide firm dates until we can tie radioactive dates to those fossils. If I can use my radioactive dating method to figure out this fossil only existed for this 2 million year span of time, then every time I find that fossil anywhere else, I will know this rock or this other fossil is within that 2 million year span of time. Okay? Event stratigraphy. This is when something happened that leaves a marker of some kind. Okay? Something that's present in the stratigraphic layers that we can correlate across distances, very similar to how we use fossils. This mean anything like a volcanic ash bed, something like this. Okay? The Long Valley volcano here in western Nevada erupted and spread ash across this entire place. Everywhere you see this yellow bubble, the ash went. Do you remember the picture of Yellowstone? The Yellowstone volcano eruption? How far the ash went? Yeah, right here. I still have it open. Look how far all of these ash went. See? Here's Long Valley caldera right there. It's the one we were just looking at, right? Right here. Spread ash all over here. This is where Yellowstone is right now. Spread ash all over here the last time it erupted. Marker beds. I can dig here, or here, or here, or here, and I will find the same layer of ash. Right? Meteorite or asteroid impacts do something similar. The asteroid that killed the dinosaurs spread ash all across the planet. I can go to Montana, Antarctica, and Germany. Dig into the rock and find the same marker bed from that impact. Okay? Then there's unconformities, they're called. An unconformity is when some amount of rock has been weathered away and then other rock deposited on top of it. And it makes a really weird discontinuous sequence. Okay? This is a disconformity when I have layers of sedimentary rock that were deposited and then weathered. See this weathering surface here? And then more sedimentary rock piled on top of it. So when I'm looking at this in a stratigraphic column, I'm not going to see a nice flat horizontal line between my layers. I'm going to see this weathering surface. That's called a disconformity. A nonconformity is when the same thing happens but on an igneous or metamorphic surface. See, here's my weathering surface, and then sedimentary layers piled on top of that. A paraconformity, this can be tricky. A paraconformity is when I have horizontal layers of rock that get weathered, or that get built up, deposited, and then weathering takes it down along a flat surface. Or, and this is where it gets even trickier, there's simply no deposition. What if this is the bottom of a lake, right? And then that lake dries up. And then nothing gets deposited on that surface for 1,000,000 years. And then deposition picks back up again. There's going to be a 1,000,000 year difference in time between that layer and that layer. That is a paraconformity. That missing time is called a paraconformity. And then we have an angular unconformity, which is when I have layers of rock that are deposited horizontally and then tectonically tilted and then weathered and then horizontal sediments deposited on that. See that? Tilted beds, weathered surface, more horizontal layers deposited on that. These are all unconformities, and they are absolutely things that we have to deal with in stratigraphic studies all the time. So, now I have some data. I know some of my material underground. I know the sequence of my layers of rock. I have stratigraphic columns. What do I do next? Correlation is the next step. Knowing all the information from one place is fine. Knowing it across a whole region, much better. Right here, I'm looking at one tree, right? If I try to correlate that, I'm going to see the whole forest. Okay, so what do? I need to collect as much data as I can. I need to look at as many trees as I can to try and understand this forest. So I'm going to collect things like seismic data, where I bounce my sound waves underground and measure the rate at which they come back to see where the different layers of rock are under the ground. Okay, remember that's seismic stratigraphy. You'll make something like this out of it. Okay, and I'm going to collect core samples. And from those core samples, I can make stratigraphic columns like you did in Lab 2. Now, when I get my stratigraphic columns and my seismic data together, I can line them up. So this is my seismic data, and I took two stratigraphic columns from core samples. We drilled down here at this location and here at this location, and then we did a seismic study of the area, and we got this map. I can basically drop my stratigraphic column right here to the proper depth. Yeah. And then the other one down here to the proper depth. And I can match up what I see in my seismic profile exactly to the layers of rock here. Sandstone here, sandstone there. Very exact, like this. Then I can correlate the two to each other. If all I have are this core and none of the seismic stuff, I basically would say, let's see, where's a pen? If I were trying to match this sandstone over there, I might go, okay, so there's two big bursts of sandstone here. That might be somewhere over here, okay? Oh, wow, that pen sucks. Okay, I might draw my lines like this. Without the seismic data, that might seem totally plausible. But guess what? I have seismic data. That seismic data lets me follow this sandstone layer down here. And if I were an oil company who thought that sandstone layer might have oil in it, this is extremely valuable. I can see the picture between the two. This is correlation. And the more data you have, the more exact your correlation can be. Now, some of the things that we can see preserved in stratigraphic sequences are large-scale environmental changes. Things like temperature change. What causes temperature change? Well, there's a lot of things that might cause temperature change. Most commonly, Milankovitch cycles. Do you remember Milankovitch cycles from 1403? Anyone? Milankovitch cycles? Allow me to refresh your memory then. Here we have a marble, a big blue one. We like this one. This is a good marble. It moves around our sun, right? Or does the sun move around us? I can never remember. Which one is it? Okay, good. I was seeing who was awake here. All right. Okay, so we're moving around the sun in a couple of different ways. The first one is our eccentricity. That is our actual orbit around the sun, not circular. Okay? It is not a circular orbit. If it were circular, we would not have seasonality. Okay? Instead, how long does it take us to go around the sun, guys? About 365 days, give or take. Okay? Instead, we have an eccentric orbit. Okay? We have an elliptical orbit, where we go in this kind of, I have the picture back here. We have this eccentric or elliptical orbit, where we make this sort of egg-shaped orbit around the sun. It is not always like that, though. We vary on about 100,000-year cycle between ever so slightly more circular and more elliptical. And this mostly has to do with the occasional pull of other large gravitational objects in our solar system, like Jupiter. Every now and then, Jupiter is just close enough that it pulls us a little further from the sun. And then it's too far away, and our orbit becomes more circular. Okay? So that happens. Then we get, let's go back to the current slide we're on. Then we get obliquity. Notice that Earth is on this tilt. It is tilted, right? And it's spinning on that tilt, on that axis. I need to grease this planet. Okay? Then we have our precession, where we are wobbling back and forth like this. So Earth is doing this around our sun.
Not that fast.
It's not that fast. I'm speeding it up. I can't go at scale. It's actually way faster. We're moving several 100,000 miles an hour.
Wait, right now,
Yeah.
we're moving 1,000 miles.
We're moving hundreds of thousands of miles an hour through space right now.
Notice how I don't feel it?
Yeah, I know. Yeah, we don't feel it. Do you want to feel it?
Oh,
Yeah.
we'll die, right?
Yeah, you would die.
You get sent off the wall. Yeah, I saw a video
Like
talking about,
if we feel all that
Huh?
I saw a video saying that if the world started just sucking, we'll all just just like we'll just get thrown.
I mean, no, because gravity. Earth is still the strongest force of gravity on us, right? I can't even begin to theorize what would happen if Earth stopped moving. It never would. For Earth to stop moving, the sun's gravity would have to no longer exist, and we're all doomed anyway, right? Like, that's far too big a thing to even begin to theorize. Yes?
Okay, I had a similar conversation with my mom. I was thinking, let's say Earth is going this way. If you're on this side of the Earth and it stops, people think you're just going to go flying off. What if you're on the other side? You would keep moving in that direction into Earth. Which
I
is
mean,
like flat.
Yeah. I mean, if that first thing happened, then yeah, logically the other thing would happen, right? I don't think that would be the case, though. Without the sun, Earth still has gravity. Bless you. Besides, momentum means something totally different in space than it does here. There isn't a medium we are traveling through in space. Yeah.
So we like all fly in one direction?
I'm saying I don't think that would happen.
If that did, we could like just like put ourselves in like a Superman pose and fly around the world.
You'd burn up in the atmosphere before you even made it to space.
So if the Earth is spinning as fast as it is, and it just stops when we go flying,
Stop spinning?
yeah, it's like it stops dead in its tracks.
No, we'd be pretty discombobulated, though.
So we wouldn't like fall or.
No, we'd all we'd probably fall down. Like, I don't even know if we'd be able to pick ourselves up and walk. Like, we'd be extremely, not heavy, not heavy, because it wouldn't change gravity. What it would change, though, is the day-night cycles. Our spin is the day-night cycle, right? So without Earth's spin, the same side of our planet would always be facing the sun.
Whatever.
Yeah. Yeah, one half of our planet would start getting crispy, and the other half would get cold. That's what happens to other planets, by the way. Our moon does not spin. You guys know that? The same side of the moon is always facing Earth.
No.
Yeah?
I thought the planet is just locked.
It's what?
I thought it was just locked.
What do you mean locked?
So like it spins at the same speed as like circles.
Okay, so no. That's different. That's different. The same side is always facing us as it spins around us. It's orbiting us at the same rate that we are spinning. So the same side is always facing us. Okay? That's why you ever heard the term the dark side of the moon? That's the other side, except that's not correct, right? Because when we have a dark moon, when we have a new moon, there is no moon in the sky because it's all dark to us. That means that the other side is completely bathed in light. So the dark side of the moon is not actually always the dark side of the moon. When it's a full moon to us, that means that the sun is shining on the whole side facing us and the other side is dark. It goes in a 2-week cycle. 2 weeks of dark, 2 weeks of light for the moon. That's why we have monthly changes back and forth. Every month we'll have a full moon. Every month on a offset 2-week cycle we have a new moon.
I feel like we had one either like last night or this morning.
Yeah, we had a full moon last night or the night before. I don't remember. I think it was last night. Yeah.
Wow.
was in the car.
Well,
Changing what?
good job.
Do you mean like mass? That's an interesting question. Can we change the mass of the Earth enough to affect any of this? No. Earth has been picking up, space is not empty. Space is filled with cosmic dust from when our solar system was made, right? We pick up hundreds of tons of cosmic dust as we fly through space on our planet every day, right? Hundreds of tons every day. It has never been enough to substantially change the way that Earth's orbit behaves. Same with the moon. Now the moon is ever so slightly moving further and further away from the Earth. It's way further than it was during the time of the dinosaurs. It's way closer right now than it will be in another 100 million years. But I don't think it's ever going to reach the point where it can fully escape Earth's gravity. I'm not confident in that. But the math seems to suggest that it likely won't. It will just be far enough away, it's going to look smaller. Yeah?
So when the dinosaurs were here, the waves were like bigger because the moon was so close.
Were the waves bigger? Don't know about that. The tides were definitely going to be stronger, though. Waves are not controlled by the moon. Tides are. Yeah. Yeah.
Wave and a tide.
Tidal action would have been a little stronger because of the proximity of the moon. Yeah. Okay. Have you guys ever seen Interstellar?
Yes.
Yeah.
Do you remember when they're on that planet next to the black hole? They're on the planet next to the black hole. What happened?
Time gets slower for them.
Sure, time, but I'm talking about tidal forces.
Oh.
You remember the wave?
Oh, no, hi.
Yeah, it was a massive wave, like thousands of feet high. Why? Because the black hole was so close, it had a tidal force so powerful, it sucked most of the ocean from this planet up into this giant wave that would circle the planet. As the planet rotated around the black hole, the wave would circle around the planet, following whichever side was facing the black hole. Right?
So would it be smaller in some spots?
There was just the one wave.
Yeah, realistic.
Yeah, that would be pretty realistic. Because, I mean, what is a tide? On Earth, it's a bulge of water that is pulled towards the moon. Right? If you had a black hole anywhere nearby, that is an incredibly powerful gravimetric force. And so it is going to pull most of the water towards itself. Not enough to pull the water out into space, but yeah, you'll get this massive surge of water that's just going to be essentially remaining in place, being pulled towards the black hole while the planet is rotating underneath of it, making the effect of a wave. The wave wasn't actually moving. The planet was moving underneath the wave because of all the water that was being pulled towards the moon, or the black hole.
What would happen if we got sucked into a black hole? We die.
Good question. I've told you all about spaghettification before, I think. You get spaghettified.
You like stretch out?
Yeah, you'd stretch out. Your body would get stretched out. It might feel nice at first, but eventually, it's going to start getting painful pretty quick. And then as the atoms at the end of your feet are getting pulled into the black hole faster than the atoms at the top of your head, your body is going to stretch, and then eventually it's actually going to snap, probably somewhere around the middle lower back around here, above your hips. Your body would snap in half, and then your atoms would get stretched away from each other as they are pulled into the black hole piece by piece, and then your top half of your body would get pulled in as well.
Oh, that's nice.
Yep. Did you have a question, Gavin?
I was gonna say, what if you're on anesthesia?
Oh,
Anesthesia under
the same thing would happen. You just wouldn't feel it.
Yeah, but would it be cooler?
Oh, wait, are you talking about conscious?
Yeah.
Oh, so you're under. Okay, so you got like some sort of painkiller in your system. I don't think that would be enough to keep you from getting snapped in half. And besides, that wouldn't keep you alive, right? Your body gets snapped in half, you're going to die pretty quick. Now, do you die before the black hole finishes spaghettifying you? Do you die from your wound before the black hole finishes spaghettifying you? I don't know.
I feel like it would like
Try it and let me know what happens.
suck all your blood out.
It would. It would turn your entire body into a string of atoms.
I feel like you would die before you went inside.
You would. Your body would not be able to take those forces beforehand. This is all theoretical. If you could survive to the point where a black hole would pull you in. But I mean, think about it. You're in space. Your ship has already obviously been ripped apart. If your body is getting pulled into the black hole, you're dead way before this could happen. In reality, this is all hypothetical. Okay. Now, these changes in temperature can set off positive feedback loops. A positive feedback loop, or a cascade effect, is a similar thing, okay? It's where one thing happens and another thing happens and another thing happens. Cascade effects are consequences. These can feed into positive feedback loops. What a positive feedback loop is, when a consequence feeds the original action or process. Glaciation, for example, or global warming. Global warming is the one that we're going through right now, so let's talk about that. What happens if Earth's temperatures heat up? What happens to our snow line?
Oh, it goes down.
Snow line goes up. Snow line goes up, less glaciers are above the snow line. Less glaciers are above the snow line, more ice melts. More ice melts, sea levels rise. Sea levels rise, less ice at the caps. Less ice at the caps, less reflected radiation. Less reflected radiation, more radiation remains here. More radiation remains here, hotter temperatures. Hotter temperatures, snow line continues to rise. Positive feedback loop. It keeps feeding itself. Okay? We can see these. We can see these sequences of higher sea levels, of hotter temperatures in the geologic record. Check this out. Transgression and regression. You remember this? Transgression, sea level rise. Regression, sea level fall. We can see this in the fossil record or in the geologic record. How? Because different types of rock are deposited in different depths of water. If I see sand, I'm going to assume shallow water, beach environment. If I see limestone, I'm going to assume, something like a warm, shallow sea. If I see shale, I'm going to assume deep water. So if I'm looking at my sequences of rock, aka the stratigraphy, and the order that those layers of rock appear in, I can make an interpretation of what sea level was doing at that point in time through that sequence. Okay, so for example, whenever sea level is falling, I'm going to see, let's do this one right here, okay? I'm going to see deep sediments underneath of shallow sediments, okay? So sand would be on top of shale and on top of limestone if sea level's falling, because my beach is essentially moving further out into the ocean as my sea level is falling. As my sea level is rising, I'm going to see the opposite effect. I'm going to see deep sediments on top of shallow sediments, because my beach is moving further inland and my deep water is moving further after it. So as it zigzags back and forth, I'm going to see this trend, okay? So lagoon sediments on top of barrier island sediments on top of deep ocean sediments, that's going to be regression. Barrier island sediments on top of lagoon sediments, that's going to be a transgression. And then we can see them go back and forth, right? If I were to drill a cross section right here, I would see a transgressive sequence, or excuse me, a regressive sequence on top of a transgressive sequence, like this, right there. Okay? Let's see this in real life. This is what it actually looks like. These are what the layers of rock in a stratigraphic interpretation, very generalized, are going to look like underneath of Paris, France. Paris has been out of the ocean for a while, right? It's covered in non-marine sediments. In this particular thing, the purple are non-marine and the yellow are marine, okay? It has been out of the water for a while, so it's sitting on top of non-marine sediments. Underneath of that is marine sediment. What does that mean? If marine sediment was there, what must have been there as well? The ocean. The ocean was sitting there where Paris is right now. As a matter of fact, Paris was under pretty deep water. Look how far out this way the sediment goes. Okay? Before that, there was a regression. Then little transgressions, regressions, transgressions, regressions. Pretty big transgression where the ocean came and covered the land. Regression, transgression, regression, transgression, regression, transgression, regression, transgression, regression, transgression. That's what that means. The zigzag back and forth in my stratigraphic column. Are you going to make a diss track of me saying that now? The zigzag back and forth of the marine and non-marine sediments is what lets me see what the change in sea level was through time. It's pretty cool. Major interpretation tool for piecing together the history of our planet. All right. Any questions on today's lecture? Great. Exquisite. I got exquisite, guys. I have reached a new peak. I cannot go any further. All right, I'm going to end the recording here. Please feel free to continue working on labs 2 and 3. Definitely 2, if you have not turned in by now, absolutely get it in today. 3, you should be starting on already, because you're going to be getting 4 next week.